Hey class, this is Mr. Durst here, and we are going to start our discussion on chemistry. So let's dive into it. As we look at chemistry, let's think of an element. What an element is the simplest form of matter that has the same chemical and physical properties. I like to think of gold as an example. Whenever you're looking with gold, you can't break gold down to something simpler than gold and still have an element. So when we look at gold, it's shiny, it has some specific luster, it has some specific malleability, it has a specific color, it has some specific electrical conductivity. And if you take that piece of gold and cut it up into little pieces, the smallest piece of gold with the chemical and physical properties of gold is called an atom. So that's the smallest piece of an element that has the properties of that element. And one of the key things about atoms is that every atom will have the exact same number of protons in its nucleus. And that number of protons in the nucleus is referred to as the atomic number. And within human biology and human anatomy and physiology, we have 24 elements that have a very significant biological role. 6 elements make up the vast majority of our bodies. And we can think of those as oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus, or SHNAPS, as I like to think of for my abbreviation. And then there's going to be 18 trace elements. Those are things like copper or iron or selenium, things that are present in very minute quantities in the body, but needed for very specific functions, primarily as enzyme cofactors within our bodies. Clear the screen. There we go. So let's think of minerals. When we think of a mineral, this is going to be typically just a pure metallic element within our bodies. From a nutritional sense. So these inorganic elements, and when we say inorganic, mean there is no carbon, generally speaking, associated with the minerals. And these minerals are taken up by plants, the producers within our ecosystem, and then passed up to us through the food chain. Common minerals that are present in our bodies include calcium, phosphorus, chloride, magnesium, potassium, sodium, and sulfur. So these are some of those trace elements. And they make about 4-ish% of our body weight overall. And when we think of these minerals, they're very important for us for body structure. For example, we have calcium crystals in our teeth and bones, etc., etc. When we think of these minerals, zinc fingers, for example, is one of my favorite examples of a mineral that's needed for an enzyme to function properly. So we have a zinc ion that's needed for some enzymes to access our nuclear code or our genetic code with the zinc fingers. Sometimes when these minerals are dissolved in water, they can conduct electricity, and those are referred to as electrolytes. Electrolytes are going to be the mineral salts or the dissolved minerals that we need for our nervous and muscular systems to function properly. Now, if we have something dissolved in water and it gains or loses an electron, it has a charge to it. We refer to it as an ion. So electrolytes by default are going to be ions. They can be an atom or a molecule with an unequal number of protons and electrons. And we haven't talked about electrons yet. That's prerequisite for this class, but just to review, electrons have a -1 charge, protons have a +1 charge. So if we have an unequal number of them, then the charge of that atom or molecule will be something other than 0, either greater than or less than. Ionization is the process of moving or transferring electrons from one atom to another atom. And if an atom has gained an electron, it has an overall negative charge, and it's going to be called an anion. If it has lost an electron, it has an overall positive charge, and is referred to as a cation. And as we look at these ions with opposite charges, they oftentimes will be attracted to each other. Positive charges are going to be attracted to negative charges. So as we look at the electrolytes that we need for our muscular and nervous systems to function are going to be able to ionize in water. So when we look at these ionic compounds, they dissolve in water, they form ionic compounds, and then they can conduct electricity. We use electrolytes for many different things, including modulating chemical reactivity, osmotic balance, and the electrical conduction with our muscular and nervous tissues. When we look at electrolyte balance, it's very important for our bodies. If we have too many or too few, you can have abnormal cardiac rhythms, you can have abnormal brain functions, you can have abnormal water balance within the body. So we need to maintain electrolyte balance within our bodies and within your future patients' bodies as well. As we look at our chemical bonds are going to be an attraction between two or more atoms. So as we have this attraction occur, many times we're going to have a molecule form. And I don't want to get into the distinction between crystalline compounds versus covalent crystalline, ionic crystalline, covalent molecular. Take a chemistry class. This is anatomy and physiology. So we're just going to say chemical bonds hold atoms together within a molecule or can attract multiple molecules to each other. We also can have ionic bonds, which are a kind of chemical bond, and those are going to be the attractions between positive and negative ions. And as we look at our ionic bonds are formed from ions, so we have electrons being transferred, and something to emphasize here is that they're easily broken by water. Ionic compounds, by definition, can be easily dissolved within water. So as we look at our electrolytes are generally speaking all going to be ionic compounds because they can dissolve in water. Oops. There we go. We can have covalent bonds as well. The two kinds we're going to talk about are nonpolar covalent bonds and polar covalent bonds. These nonpolar covalent bonds are going to involve shared electrons, equal sharing of electrons. So here we have a hydrogen molecule, and because each atom within this molecule is exactly the same, we're going to have the electrons shared halfway between them because they have equal electronegativities. If we have a polar covalent bond, the electrons are going to be shared unequally. The most common highly electronegative compound that's going to be associated with these polar covalent bonds is going to be oxygen. And in this situation, we could have, if it was an unequal sharing, these two electrons would be scooted a little bit farther over to the nucleus of one atom and farther away from the nucleus of the other atom. That would be an unequal sharing or a polar covalent bond. And as we have polar covalent bonds involving oxygen, particularly oxygen-hydrogen bonds and oxygen-nitrogen bonds, we find that we can have hydrogen bonding occur. And this hydrogen bonding is kind of unique in that it's an intermolecular bond as opposed to an intramolecular bond. What do I mean by that? I mean that it's a bond between separate molecules. So here we have some dotted lines, and those dotted lines represent the intermolecular bond. That is a hydrogen bond between a slightly negative oxygen, and we have a, as I clear my screen here, you can see there's that delta L, or that negative delta. Let me draw it up here, lowercase delta minus. We have a partial negative oxygen, and here at the hydrogen, you can see in the figure a delta positive, which stands for a partial positive charge. A partial negative plus a partial positive results in that hydrogen bond in between the two atoms of two separate molecules. One hydrogen bond by itself is not that strong. Ionic bonds are stronger and covalent bonds are stronger than hydrogen bonds. But the key thing about hydrogen bonding is that there's power in numbers, and you can have them build up and accumulate force. And as we look at things like DNA or proteins, hydrogen bonds within the DNA of our bodies, or the proteins of our body, play a very significant role in the overall structure of those large macromolecules. That's all we have for this recording. If you have any questions, please feel free to post them on the class discussion board or shoot me an email. And as always, happy studies.